Welcome back everyone to applications of logarithmic functions, and I promise you this video is a lot shorter than the last applications one, and easier. So let's start by opening it up. So logarithms basically are useful in the sciences because they take very small numbers and very large numbers and just make them easier to work with. For instance, I have an example here of the Richter scale, which you guys may have heard of before. It's basically for measuring how strong is an earthquake. Earthquake! So how strong is an earthquake? So you have your magnitudes. Magnitudes are just from -1, apparently, to 9. And then you've got your actual kind of intensity. So notice that every time you go up one magnitude, like from 6 to 7, your earthquake is actually 10 times stronger each time. So times 10 as you go up. So between a magnitude 7 and magnitude 8 earthquake, it's an actually 10 times stronger earthquake. So instead of having a number like 10 to the 8th power, which is first power, second, third, fourth, fifth, sixth, seventh, eighth. So instead of working with this number, you can work with the number 8. I don't know about you, but I prefer to work with the number 8 rather than that one. So, log scale in action, basically. Another example is the decibel scale, which is kind of how loud a sound is. So, loudness, so to speak. You can see from this scale that, for instance, I have the sound pressure in micropascals. It goes up by 10, but the decibel only goes up by, that's about 14, and that's about 34. It only goes up by 20. So basically every time these go up by 20 or so, the sound pressure actually multiplies by 10. So instead of working with a number like 1,000, I can have the number 34. So that's basically what a log scale does for you. It just brings your numbers closer together to a more manageable size. So the example that we're actually going to be doing calculations with is pH, so the acidity of a substance. And you've got your pH, which is basically the negative power of 10. So if something has a pH of 4, that means it's basically 10 to the negative 4th power is your concentration of hydrogen ions. So let's actually go over the formula. So H plus stands for your hydrogen ion concentration. And be real careful that you don't ever leave off that negative sign. And then your pH, of course, is the acidity. So this is not two variables being multiplied together. This is just your pH. Acidity, or how basic it is, or and so on. So let's check out our example problems. So find the hydrogen ion concentration of a substance that has a pH of 13.5. Okay, so I know my pH is 13.5, so 13.5 equals negative log of H plus, and H plus is my variable. So first thing you have to do is get rid of that negative sign. So you could think of it as dividing by -1. So I have negative 13.5 equals log of H plus. And then remember that a log without a base is base 10. So basically what I've got here, I'm going to turn it into my exponential form. I've got 10 to the power of negative 13.5 equals my hydrogen ion concentration, which comes out to, all right, so 10 to the negative 13.5, press enter, and we get scientific notation. So let's write that down. So 3.16, I'm going to round it, times 10 to the negative 14th. Well, let's see if it's going to... I was kind of hoping it would write it out. But you know what? Let's see what that number's like. Let's do this, shall we? So 3.16. Now, remember scientific notation means you move essentially you're moving your decimal point 14 places to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so something with a pH of 13.5 has a hydrogen ion concentration of this. Now, which number would you rather work with? 13.5 or this? I don't know about you. I'd rather work with 13.5. So that's what a logarithm does for you. It takes this crazy whatever this is and, 13.5. Isn't that nice? Let's try a couple more. They won't be quite as bad as this one. So we're going to find the hydrogen ion concentration of a substance that has a pH of 7. So 7 equals negative log of H plus. Some of you are going to see a shortcut here. Just make the pH negative and do 10 to that power. That's really all we're doing. So of course divide by negative 1 again. So you get negative 7 equals log H plus. And then turn that into an exponential form. So 10 to the negative 7th equals your H plus. And then H plus equals... Now, if you put this in your calculator, which I did, just to see what would happen, it gives you a fraction. Still, that's not nearly as bad looking as this. But would you rather work with this number or with the number 7? I would rather work with the number 7. And that's what a logarithm does for you. So let's go ahead and put the fraction. Why not? Of course it does. Duh. 7. All right. Cool. One more. Find the hydrogen ion concentration of a substance that has a pH of 2.3. Now this one again is going to be much less nasty than the other two because the pH is getting closer to 0. So 2.3 equals negative log of H plus. Divide by negative 1 on both sides just like we did up here. So you get negative 2.3 equals log of H plus. Turn that into exponential form. 10 to the negative 2.3 power equals H plus. And when you put that in your calculator, you get approximately, and I did round it here, approximately 0.005. Now, again, this is not nearly so bad as either of those, especially that one. But still, 2.3 is a much easier number to work with than this. So that is the application of logarithms, basically taking really messy looking numbers in the sciences and making them more manageable. So go ahead and pick up your assignment for this, and don't forget to let me know you're ready for small group.